All right. Hello, everyone. Welcome to class. Today's discussion is precisely 11.2, 11.2, and that is series. And in 11.1, we started discussion about sequences, which was the foundation. So we are taking it a step further by studying series. Okay. So let's make some definition. First definition I like to define is about an infinite series. So if we have an infinite sequence, then the sum of terms, okay? So when we talk about series, we're summing up terms actually, okay? So then the sum of terms and the sum of the terms of the sequence A1 plus A2 plus A3, on and on. Of course, you can have the nth term, but it's an infinite sequence, right? So it's endless. Okay. If this guy is an infinite sequence, then the sum of the sequence is actually called an infinite series. Okay. Or sometimes it can just be called a series. So if you don't call it an infinite series, you just call it a series. And it is denoted by, okay, so now we want to look at the notation. This is a notation, n from 1 to infinity of an. Okay, so if you have, now for instance, we studied sequences in 11.1, right? And we said this is the list. So this sequence is just, you have a A1, A2, A3, on and on, right? But at the level of series, you have the summation sign, but you still have this an. So this is like n from 1 to infinity. And this is going to be, now what does summation do? It sums up the term for you, right? So this is just going to be A1 plus A2 plus, you keep going on and on. All right. So now another thing we need to actually, talk about or to look at is what we call the nth partial sums, or in some textbook, it can be referred to as the sequence of partial sums. Okay. So let us say denotes. Usually we use S sub n. You know this guy, as I goes from 1 to n, AI. So this guy is just A1, A2 up until AN. Okay. So this guy is actually called, this is called the nth partial sum of the series. Okay, now let me explain what this means, guys. Now over here, let me pick a red pen. Over here, we say this guy is a series, right? You add up each term. You had A1 plus A2 plus up to AN, then you continue, right? Now the first nth guy here is what we call the nth partial sum, because it starts at the first one but ends at the nth position. Okay, so this guy is just going to be my Sn. Okay, so that's what we call the nth partial sum of the series. Now we want to ask a question. And what's this question we actually want to ask? Now, how do we know the sum of all terms? Okay, how do we know the sum of all the terms? Now, what is the answer? The answer is that we study the behavior of the sequence Sn of its partial sums. Okay, we're going to see what this actually really means. Okay, now consider S1, which is the first term. What is going to be S2? Now these are sum, right? So this is going to be A1 plus A2. What is going to be S3? That means you have to sum up 3 terms. I can continue. What is going to be Sn? Sn means I'm going to sum up the nth terms, right? Or I mean n terms. So you have this guy, it's I from 1 to n, and this is AI. Okay. So let me just write that these partial sums actually form a new sequence. Okay, so this is just like a further explanation to what I just gave above. These partial sums form a new sequence, which is denoted this way. Okay. Called the sequence of partial sums. All right. And we can write this guy, if you have I from 1 to infinity, you can write this guy as the limit as n goes large of Sn. Okay, so let me box this guy. All right, so we're going to learn a couple of definition here, because we're laying in this section, we're laying the foundation for our series. Okay, we're laying a foundation for the series. We're going to study different series tests and the likes. So definition. Now, if this sequence of its partial sums, if it is convergent, okay, and if the limits as n goes large of this same sequence of its partial sums, if it is equal to S. Okay, so S is a real number. S is a real number. Now remember, when do we say the limit exists or limits of a sequence exists? It exists when you find the limit, it gives you a finite number, right? Okay. So then, this is another definition. We say that this guy, n from 1 to infinity, is convergent. Now, what does this mean? It means that a series is convergent if the sequence of its partial sums converges. Can I say that again? A series is convergent if the sequence of its partial sum converges. So probably I'm going to write that. I'm going to write that down in red. So I'm going to put in a bracket, parenthesis, I mean, a series converges if the sequence of its partial sums converges. Okay. All right, so let's move forward. So if this series, we want to this guy, if it is convergent, we write this guy, the sum itself, write it equals S, where this S is the sum of the series. Okay, so now what are we saying here? We're saying that if you have some kind of series, if you're given a series, it is possible to find the sum. Okay, if I give you an example, if I say sum 1 to 5, okay, that means you do 1 plus 2 plus 3 plus 4 plus 5. Okay, so that means I have the sum. But there are other series where such kind of S does not exist. Okay, and that's when we'll talk about the series as being divergent. So let me write that down. Otherwise, this guy is divergent. So the idea of divergence is just the opposite, exact opposite of the concept of convergence. Okay, so that's just the exact idea. Okay, it's the opposite of the convergence. Let me give you a quick example over here. Example, suppose we have a series n from 1 to infinity of an, whose nth partial sum is, you have Sn equals, you have 5n plus 4 divided by 2n plus 6. So the question we're trying to answer is that find this series, find the sum of the an. Now, what do we do? Solution. Okay, so what do we do? Remember that we just saw right on top. Let me back up and show you guys. This guy in box, we see that this series is just equal to the limits as n goes to infinity of the sequence of its partial sum. Okay, this guy in red box. So, and that's the same thing we're going to do here. So we remember that this guy is just the same thing as the limit as n goes large of Sn. What is Sn? Sn is given. So I'm just going to do limit as n goes large of 5n plus 4 divided by 2n plus 6. If you compute this limit, what do you get? You just get that 5 over 2. So what does that mean? That means, so this guy is just going to be 5 over 2. Okay, makes sense. Now, in this case, now you're given what Sn is. But in some other cases, it's pretty much not easy to find an expression for the sequence of partial sums. Okay, so sometimes it is not easy. Okay, so now let's start the discussion about some famous series. Okay, so we have, we're going to just discuss just the famous ones. We have a different kind of series. We'll discuss the famous one over here. Okay, discuss a couple of them. Let's just move on. So let me just come here and just say, maybe I just say, okay, let me just start from the first one I'd like to talk about is the geometric series. So theorem. The geometric series. Okay, I'll give you an example. You have the first term A plus AR plus AR squared plus AR cubed. If you continue on and on, this guy, I can write this guy in terms using the sum, the notation, the sigma notation. Now, how do I use the sigma notation? Of course, I know it's an infinite sum. So I can start this guy from n from 1 to infinity. Now the a is not changing, right? A is just a constant. So I just have an a. But what about the r? The r is changing, the power is increasing. Over here, r is 1, r is 2, r is 3. So that means you have r to the power of something, right? So pretty much that is going to be like n minus 1. Now let's see. When n is 1, what happens? You have a ar to the power of 0. What is r to the power of 0? That's 1. So you just have a. And this corresponds to this guy. Okay. Now, in some textbook, the geometric series is written as this guy. The only difference is that you're starting this guy from 0. If you start calibrating this guy from 0, go to infinity, this is going to be ARN. Okay, so these two guys are equivalent. When you start your n from 1, you have ARN to the power of AR, then you have n to the power of n minus 1. I mean, sorry about that. And then when you start it from 0, your power is just n. Okay, so both are actually the same. So I need to actually mention that this guy, so you have n from 1 to infinity, ARN minus 1. Okay, so I need to put a caveat here that your A is non-zero. This guy is convergent. If the common ratio, R is called the common ratio, okay? The R is what we call the common ratio, okay? All right. So when the common ratio is less than 1, and its sum is, now what do we mean by sum? Remember, a very easy example is like, I tell you to do just sum 1 to 5, okay? 1 plus 2 plus 3 plus 4 plus 5. Okay, that's the sum. So like the exact value. And the sum is, you have a sigma notation from n from 1 to infinity, AR to the n minus 1. This is given by A divided by 1 minus R. Again, the caveat is that this guy has to be less than 1. So what does this mean? It means that a geometric series, right, converges if the common ratio is less than 1. Okay, so you have to be familiar with a couple of things in chapter 11. Okay, so my encouragement is going to be that you should try to get like make your formula sheets. There's going or have like note cards. Yes, so have note cards where you have your definitions written. You have your note cards where you have your the different kind of tests and how to apply them. Okay, because when we talk about geometric series, the convergence of geometric series is based off the fact that the common ratio is less than 1. Okay, so but we have a question. Okay, what if the common ratio is bigger than 1? Or what if it is equal to 1? That's when we have greater than or equal to. The geometric series is divergent. Okay, so when that happens, you have some form of divergence. Make sense? All right, so I think it's a good time to jump on some examples that bother us on this one. I have to jump on some example and see how it works. Okay. Example. is the series. You have this guy, n from 0 to infinity. This is 3, 2 over 5 to the power of n. Is this guy convergent or divergent? Is this series convergent or divergent? Let us check. Solution. Now keep in mind, right, guys, that a geometric series converges. So keep in mind that a geometric series converges if what? The common the absolute value of the common ratio is less than 1. Okay, so and then also we can find the sum. And its sum is given by a divided by 1 minus r, right? Okay, let us see. Now, how does the geometric series look like? Remember, we had 2 different forms depending on what you have. This is 3, 2 over 5. Let's write the general form first. Remember, when you start from n equals 0, this guy is going to be the power on r is just going to be n. But if you start this guy from n equals 1, this guy is going to be n minus 1. Okay? So, but what is the question? The question is infinity. This is 3, 2 over 5 n. Now, can we do some kind of, comparison? Compare this general guy with this guy. That means this guy is 3. And what is your r? Your r is 2 over 5. So this is a geometric series with what? First term equals 3, and the common ratio is 2 over 5. Now, but keep in mind, when do we know that it converges? It converges when this guy is less than 1. Okay? And what do we say, guys? 2 over 5. This guy is positive, right? 2 over 5. This guy less than 1. So what do we say? First off, we say this guy converges. Why? Since 2 over 5 is less than 1. But then can we find a sum? Now, if it converges, then you can find the sum. How do you find the sum? The sum is a divided by 1 minus r. But your a is 3, your r is 2 over 5. Okay, so let's do the algebra. 5 over 5 minus 2 over 5. So you have a 3 on top and 3 over 5 on the bottom. So this is exactly just going to be 5. So this guy is a geometric series which converges, and the sum is exactly 5. Okay, makes sense? Let's see another example. You're going from 1 to infinity. Okay, so that is the 2 to the power of 2n, 3 to 1 minus n. So the question again is convergent or divergent. So this is still what we're trying to investigate. Does it converge or does it diverge? Okay, well, we'll see. Solution. Now, whatever form it looks like, you want to write it like the general form for the geometric series. Okay, when you're calibrating from 1, you want to have something like this. So how can I modify this guy or simplify this guy to look like this? That's my goal. That's the first goal I need to achieve. So let's watch. And from 1 to infinity, you got a 2 to the power of 2n. I have a 3, 1 minus n. Okay, this gets interesting, guys, because the first time here is a, right? A doesn't have a power, The only thing that has a power is r. So what do? Let's just see. Let's do some kind of simplification. This is 2 squared to the power of n. Okay, you have 2 to the power of 2n. You can write it in this form. And this is 3 to the power of, now this guy is n minus 1. If you have 1 minus n, guys, this is the same thing as n minus 1, right? Yes. So you have negative n minus 1. It's getting interesting. So what can I see? I see that what is 2 squared? 2 squared is 4, right? Now 4 to the power of n. And then you have 3 to the power of negative n minus 1. Can I ask you a question? If you have something like 5 to the power of negative 2, what happens? This negative is the reciprocal. This becomes 1 over 5 squared. Okay, so having that in mind, we're going to use it right now. N from 1 to infinity. All right, so this is going to be 4 to the power of n on the top. But think about the other guy, the reciprocal forces it down. So this is 3 to the power of n minus 1. Is it still okay? Now, what are we doing so far? We're trying to rewrite, okay? Trying to make it look like what? It has to look like the geometric series, this form. So when it does look like that, then I can apply this principle, or I can apply the definition of convergence when it comes to geometric series, okay? Now remember, at the level of sequence, when you're checking convergence for sequence, the only thing you need to do is to find the limits of that sequence. But that's not exactly the same thing we do here. It's a little bit different. Okay, so here the first one we're talking about, which is like a very famous series, is the geometric series. So you'll be able to rewrite it and then see what happens. Okay. Remember, let's see what we are comparing with. We need to have a, which is a constant, and we need to have a certain r to the power of n minus 1. Now, what do? The guy on the bottom already has n minus 1, but the guy on the top doesn't have n minus 1. Then I got to introduce a trick, okay? So just watch this interesting trick. Where are we? Okay, so just introduce a 4 over 4. This is going to be 4 to the power of n divided by 3 to the power of n minus 1. Now watch this, guys. N from 1 to infinity. Now remember, I introduced a 4 over 4. Keep the 4 on the top. What about the 4 on the bottom? The 4 on the bottom, what does it do? Divided by 3 to the n minus 1. Now watch that I use the red pen for the negative 1 power. Why? Because when you have a 4 to the power of n divided by 4, this is just 4 to the n minus 1. And that's exactly, oh no, that's exactly what I did over there. All right. Okay, so guys, can you see now, what we're really close now? This is a, right? A is a constant, we know a is 4. And this guy says r to the power of n minus 1. I have n minus 1 on the top, I have n minus 1 on the bottom. So let me write this guy on the bottom word so that you don't think it's something different. N minus 1 as in the power, n minus 1 as in the power. Yes. Okay, we're good. So n from 1 to infinity. This is a 4. So let me just still maintain the consistency. This is 4. 4 to the power 3 to the power of n minus 1. All right, so talk to me now, guys. What is my a? Talk to me. All right, my a is 4. What is my r? My r is 4 over 3. Now, when does a geometric series converge, it converges. So when this guy is less than 1, we say convergent, right? When this guy is greater than or equal to 1, we say divergent. So what can you see? Absolute value of 4/3 is still 4/3. 4/3 is a number greater than 1. So what do we say? So the series, does it converge or diverge? Is what? Divergence. Okay, so at the level of geometric series, what happens? You want to make sure it looks like one of those forms. It looks like one of those forms, then you can just apply a formula. Okay. And let's move on. Let's do one more example. Find the sum of the series from 0 to infinity, x to the power of n, where this guy is less than 1. Interesting solution. What do I know? I know that this series, if I start moving from 0, when n is 0, what happens? You have x to the power of 0 plus x to the power of 1 plus x to the power of 2 plus x to the power of 3. You keep going, right? But what is x to the power of 0? It's 1. 1 plus x squared plus x cubed, on and on. But what do we know, guys? We know that we want to make sure that this guy looks like this guy. Okay, the general form of geometric series. What can you see, guys? Compare this guy and this guy that were given. What can you see? You see that your A is 1, right? So geometric series with what? A equals 1. What is R? R is just X. Now, but when does a geometric series converge? It converges again when the absolute value of R is less than 1. What is the absolute value of R? And that's the absolute value of X, right? But look at the question, guys. This condition is given. So this guy is less than 1. So what do we conclude? So the series converges. So when it converges, the next thing you need to do is to find the sum. Okay, so remember, what is the sum? The sum is just A divided by 1 minus R, right? This is the formula, A divided by 1 minus R. What is A? 1. 1 minus, what is R? X. Okay, I hope this makes sense. This is the sum. Okay, so let's talk about non-geometric series. Okay, so you might just have a question. Is it just all about geometric series? The answer is no. Okay, so let's talk about non-geometric series. What about series that I cannot write like these two guys I was trying to write, like maybe n from 0 to something or n from 1 to something? What if I cannot do that? Okay. The best way to discuss that will really be by using an example. Okay. And let's discuss the first guy we should discuss here is this series. Let me put 1 on the top. Let's pick a simple case first. N from 2 to infinity. So what do we do? Now remember, a series converges if the sequence of its partial sum converges, right? So the first thing you want to do is to write the sequence of its partial sums. Okay, that's S sub n. Now, what do we say the sequence of a partial sum is? The sum of the first n terms. Okay, that means I can write this guy as I from 1 to n, the first n. Then you have 1 divided by. Now, be careful, guys. You're counting, you're running from I, you're going from I from 1 to n. So whatever you have here has to be in terms of I. So see, it makes no sense to write something like this, 1 over n minus 1. You're running this guy from I equals 1, and this is n. So this doesn't make sense, okay? So you have to be consistent in terms of those very tiny details, okay? Because they're very important. Now, what do we do for this kind of non-geometric series? You have to use the idea of partial fractions, okay? Now you see that some of the things previously learned, we really need them right now. So I'm gonna pick this guy, I from 1 to n, 1 over I minus 1. This is the same thing as, this should be 2. We're calibrating from 2 and now 1. I goes from 2 and now 1. Okay, so in terms of partial fraction, this guy is just 1 over I minus 1 over I. So let me put it here. By partial fraction. I hope you remember how to do partial fraction, okay? But because you actually need them here. Not partial series, partial fraction. By partial fraction. Okay, that is the idea of partial fraction. So now we've been able to resolve this guy by partial fraction, right? So what do we do? I'm now going to work with this guy. So let me just give you a hint on the partial fraction guy. I'm not going to solve it because we already studied that. So what do? You pick this guy, 1 divided by I minus 1. What type is this? This is linear, right? Linear factorizable. Okay, so this is A divided by I plus B divided by I minus 1. I hope it comes to mind now. So you find the value of A and B. So let me just tell you in case you want to do it. Your A is going to be -1, and your B is going to be 1. So this is just a hint I can give. Okay. So now I'm going to return back here. Now, when I get to this level, what do I do? Okay, that's a good question. So I is going from 2 to n. Now, what we're going to use here is what is often referred to as, because this is a kind of series where term by terms, some terms are going to cancel themselves. And basically, that's called the telescoping sum. Okay, some of you would have heard that before. Some of you might be hearing it for the first time. Those are the kind of series where, some terms just kick out themselves. They cancel in pairs. So let's see how that works. Okay, so when I is 2, what happens? You have 1 divided by 2 minus 1, that's 1, right? So you have a 1 here. Minus, when I is 2, you have 1 over 2. That's a plus. When I is 3, what happens? You have a 1 over 2 minus 1 over 3, right? When I is 4, what happens? You have a 1 over 3 minus 1 over 4. You can keep going on and on until you get to the nth guy. So at the level of the nth term, okay, so let me just come down. I'll write something on the bottom. At the level of the nth term, what happens? You're adding one over n minus one over n. Now, what can we see, guys? Can you see things can cancel? This is negative 1/2 plus negative 1/2. It gets off. This guy cancels this guy. So everything is going to be canceling out themselves in that manner until the only thing that remains is just going to be the first guy and the last guy, okay? So it's going to be the first guy and the last guy. That's going to be 1 minus 1 over n. Okay. But remember that this series we're working with is the sequence of its partial sum, right? So that means Sn is just 1 minus 1 over n. Amazing. So do you remember that we actually had something like this in red, this guy? Limit as n goes large of Sn. Okay, so do you remember we had something like this? As a matter of fact, to even make it look nicer, I can just put n here so nobody gets confused. So now what am I left to do? I need to finally take the limit, right? So the limit as n goes large of the Sn, what's it going to be? Limit as n goes large of 1 minus 1 over n. So what happens? What's this limit? You just get a 1. And if you get a value such as 1, what's your conclusion going to be? It converges, okay? Convergence. So I can just say, therefore, the series is convergent and n from 2 to infinity, 1 divided by, we're working on, what was on the bottom again? N minus 1 equals 1. So note, a series whose terms cancel in pairs like this is called a telescoping sum. If you have a series whose terms actually cancel in pairs, it's pretty much called a telescoping sum. Okay. Okay, so let's see a couple of other things we should learn going forward. We should actually learn about there's a so-called test for divergence. We should learn that and some other kind of definitions. Okay. Now, theorem. Oh, let me use my black pen. Okay, so if the series this guy, if you have an infinite series that converges, then now you got to be careful as we go into this part, guys, because if you're not careful, you can mess a lot of things up. Okay, so if a series is convergent, then the limit as n goes large is 0. Okay, if a series is convergent, then the limit of a sequence, is 0. Okay, take note of that, guys. Now, the limit of a sequence and the limit of its partial sums are not the same thing. Okay. Note, if the limit of a sequence equals 0, does it mean that the series converge? Yes or no, guys? The answer is no. Okay, now let me just do a little recap at this point. If you have a series, when is a series set to converge? The first thing you need to do, pick up the sequence of its partial sums. Okay, so find the limit of the sequence of its partial sums. If that converges, then the series converge. Now we take it a step further, that if you have a series that converges, then the limit of its nth term, or the limit of its sequence, not the sequence of its partial sums, okay? The limit of a sub n gives us 0. Okay, but not the other way around. Okay, what is the other way around? That's if the limit gives us 0, does it mean it converges? The answer is no. Okay, now that will an example, a good example I can just quickly give you on that is the harmonic series. This guy is my an, right? So what is the limit as n goes large of this an? This is limit as n goes large of 1 over n, okay? And this is what? 0. But what do we know about this guy? What's the name of this series? This is called harmonic series. And what did we say about it? Harmonic series does what? It diverges. Harmonic series always diverges. Okay? So then that will lead me to actually tell you this guy is called harmonic series. So let me write it better. The series okay. This series is called the harmonic series. And it diverges. Okay. We're not going to go into the proof of that. All right. So now we can comfortably talk about what we call the test for divergence, or what is called the divergence test. We don't call it the test for divergence test. Okay. So what is this divergence test? It says that if the limit as n goes large of an, if this limit does not exist, or perhaps we can say if this limit of an is not 0, then the series is divergent. Remember that the fact that the limit of an as n goes large equals 0 does not mean that the series of an converges. Now, but what's the test of divergence? If the limit of an does not exist, or if the limit is not equal to 0, then the series is divergent. Okay. This would be good to show you these stuffs with an example. Okay, example is a series. You have a series like this guy, k plus 2. This guy is not a geometric series, so you don't have to think about geometric series right now. So as we continue to move on, we'll have more series structures that are not geometric series. Okay, they are called non-geometric series. Okay, so is this series convergent or divergent? So we need to investigate. So what do? The first thing to do is to isolate this guy. So this is like a sub k is k plus 2. You got a k up front, k plus 3 squared. Now, I want to check something, okay? So limit as k goes large, what happens? If it is not 0, if it does not exist, then by the test for divergence, this guy diverges, okay? So now I need to mention here that, guys, the test for divergence is only used to show divergence, okay? You cannot say you want to use the test for divergence and make a conclusion that the series converges. That's not true. So when you use the test for divergence, your conclusion only has to be divergence. Okay, so what is this guy going to be? It goes large. This is k plus 2, k plus 3, all squared. So how do we approach this guy? We can even first distribute this guy. You have k squared plus 2k divided by, what about this guy? You have a k squared plus 6k plus 9. Okay, so then right now, what do? We'll find the limits. What is the limit of this guy? Okay, let me show more work here. This is k squared divided by k squared, divided by the highest power of k, 2k divided by k squared, all over k squared over k squared, 6k over k squared, then you have a 9 over k squared. This guy gets off, this guy gets off. So you're left with something like limit as k goes large. I got a 1 here, plus 2 over k divided by 1 plus 6 over k plus 9 over k squared. Okay, so this is just me showing you how to. I shouldn't be doing this, but you know, it's good. This is 0, this is 0. And that limits as k goes large. It's only going to be what, guys? 1. Is 1 equal to 0? No. So by the test for divergence. Now, in some textbook, you use the acronym TFD, okay? TFD, test for divergence. The series diverges. That's a wrong spelling. The series diverges. All right. So let's go back to what the statement of the test for divergence says. Test for divergence. What do you need to check? You need to check the limits, the limit of an. If the limit of an does not equal to 0, or if it doesn't exist, then the series diverges. Now, if you have a question and say, oh, what if this limit gave us 0? What happens? That only tells us that you cannot use the test for divergence. You have to use a different test entirely to solve your problem. So if this limit gives us 0, then that means that this test is inconclusive. It doesn't really give you an information, so you don't know. It's dangerous to make a conclusion from there. You have to think about different kind of tests. In 11.3, we'll discuss the integral tests. Going forward, we will talk about tests such as ratio tests, nth root tests, and every other test that can be used in some cases. Okay. Okay, so I think I want to end this part by giving you some properties. Okay, by giving you some properties. So theorem. Let me just call them properties. Okay, so what are these properties? Let's say let's us have series. Let this guy be series, but let them be convergent series. Okay. And let C be a constant. Okay. Then the series, now think about how we had limit laws in 11.1. So here too, we have some properties, okay? And from 1 to infinity, C of an, this guy. And from 1 to infinity, and from 1 to infinity, an minus bn are all convergent. Okay, so what are we saying here? If you have convergent series, the sum of two convergent series is convergent. Okay, if you take their difference too, it is still convergent. If you multiply by a constant, it is still going to be convergent. So this is a very important. These are very important properties. So number one, just say this guy. You got to see here. Still is a constant. I can pull it out. Okay. Another one is if you have this guy. And from 1 to infinity, this is an plus this guy. And then the last part, to infinity, this is s of n minus this guy. So these are properties. Remember, if you multiply it by a constant, okay, multiply by a constant, it doesn't change the fact that it converges. If you sum it up together, it still converges. If you subtract, it still converges because these guys are convergent series, okay? Because they are convergent series, so we're free to do that. We're free to make that happen. All right. Okay, so I hope all of this makes sense, and I hope you get it. So let's just round off with an example that uses one of these properties. Find the sum of the series 1 to infinity. You got a 5 here, n plus 1 plus 1 over 2 to the power of n. Solution. Now, by property 2, right? Yes. So by property 2, I can rewrite that guy. How can I write it? I can write it as this guy. 1 to infinity, got a 5 here, and n plus 1 plus 1 over 2 to the n. Oh, no. I just did the same thing. No. So you put a plus here. Yes. Now this is correct. So that means that I can find this guy. Let me call it A. can find this guy, call it B, then sum them up together. Okay, let's see. What is A? N from 1, right? What kind of series is A? Is it a geometric series or a non-geometric series? Think about that. Okay, so that is just non-geometric, right? By property 1, what can you see? This guy, what is property 1? Let me show you 1 second. You see, I can pull out the constant, right? This is going to be pull out your constant 5, n from 1 to infinity, 1 divided by n plus 1, got n. Now, but this guy is a non-geometric series. Now, how do you solve this guy? Just like the example we did above, where you do partial fraction. So this guy itself is equal to 1. So this is 5 times 1, which is 5. Now, what about B? And from 1 to infinity, 1 over 2 to the power of n. Now, what is B? Is it a geometric series or a non-geometric series? What do you think? It is geometric, okay? So if it is geometric, what can I do? I can find the sum. Remember, it's just like A divided by 1 minus R, something like this. So if I count from n, so this is going to be, what is A? I can write this guy. Okay, keep in mind, guys, that the A is when n equals 1, right? Okay, so think about this. When n equals 1, you have 1/2. So this becomes a 1/2 on top divided by 1 minus 1/2. Why? Because list these guys, you have 1 over 2 plus 1 over 2 squared plus 1 over 2 cubed, on and on. So the common ratio is just like this guy, 2 squared divided by 2. That's you pretty much, you have something like 1/2, and then you have 1/4. If you divide them by themselves, that's like 4 divided by 2, you have 2, but remember it's a fraction, so you have 1 over 2. This is like 1/2 on the top divided by 1/2 on the bottom. What does this give us, guys? This is 1. So if you get this guy, of course, this guy is also convergent. This guy, of course, is convergent. Because if you can find its sum, then it converges, okay? Okay, so what happens? And from 1 to infinity, 5 divided by, you got n plus 1 plus 1 over 2 to the power n, right? Which is the same thing by property 2. Right, we already saw this, I'm just rewriting it. This part gave us what? 5. This part gave us 1. So 5 plus 1 gave us what? Gives us 6. Such an interesting calculation. Such an interesting one. Okay. Any questions so far? Okay. All right. So see you